Hello? Hello? I can't hear anything. Hello?
Yes, ma'am.
Hello? Yeah. Yeah. Yes. Now tell me. Is this clear to you? Can someone explain that what are we considering here with this M by Q? First of all, I think this one is clear, right? It is the energy consumed for per in Q, DRAM access. So what is in Q? Is it clear? Yes or no? Tell me. If I give this as int 4 or int 8,
Number of bits that are used to represent that int.
yes, the number of bits we are using to represent that one. That means we are int q means that quantization we have considered, and this int 4 or int 8, that representation we are using to realize our these inputs, this weights, etc. Okay, this is one thing. Next thing is that this ED, I think SIN, this is the channel inputs, number of channels, etc. I think those are clear. But what about M by Q? This is because M, why we are considering this factor? Because we are considering this one, I mean this DRAM access in the testing phase. Remember, whatever we are talking here, we are talking about low precision networks, and we are considering this one, sorry, go there. We are considering here the test time quantization. Remember, why today we will discuss about the train time quantization, and there you will understand that these factor will not be meaningful. Why I'm mentioning this, because when we are talking about M is the input bit size. Okay, and after that we are getting the weights inputs we are getting in this with this M bit. And on top of that, during the testing phase, we are applying this quantization effect. That's why in that input layer, see, that's why this is mentioning that this is the M by Q, this is a fast layer factor. This M by Q factor is taking part, or it is affecting your overall energy, overall time also. If you think about timing requirement, here we are talking about energy. That's why we incorporated this factor in energy computation part. But whatever you compute, this first layer factor will come into picture, because we have applied the, I mean, our training phase, that is quantization free. We have not applied any quantization. Whereas in our testing phase, this quantization is taking effect. That's why we have to consider this first layer factor. This is one thing. I was expecting this question. I don't know whether maybe you have already understood. Maybe it is a repetition, but still I'm repeating this part. And this two into refetch and prefetch. This is one, initially this is easy to understand, that refetch or writing and reading during the refetch. Refetch means, as I mentioned last year, we have something in the external DRAM, in this DRAM, and from that DRAM we are taking data and we are coming back to this SRAM. Then we are using that data from that SRAM, because our computing unit, if you consider it the CU, our computing unit, it can only access values from SRAM, not it directly cannot access DRAM. Okay, now here we are only considering one-time storing and accessing data. Okay, that's why we have considered this two, that twice we are just fetching this two. This is for that application, or that first initial level, that may be 2, but if you are doing multiple refetch, these 2 will change. You can generalize that with some value n will denote the time you are refetching some amount of data. That is based on your usage of your particular weight and based on the available RAM you have in your chip. This refetch factor, this two that will change. Okay, so this is this two things I wanted to clear. Rest of the parts, I think it is clear that why this refetch, reading and writing, storing actually, fetching and storing time we are considering for intermediate feature maps. You can see here we are fetching, and this part, this activation, these inputs and the output values per layer, maybe sometime we are storing here or maybe sometime we are storing back in there. So for that read, write, fetch, store, those timing we are considering, but that is we are just consider 2 into something, but that may increase based on how many times you are refetching your data. Based on refetching, again, that factor will depend on how much, what is the size of your DRAM and what is the size of your SRAM and what is the size of your application, how huge your application may be, and how many times you are reusing your some input value or some maybe weight value. So based on this factor, this is not like foolproof, this expression. That's what I wanted to mean. Okay. Then come to the total consumption. Okay. In this total consumption, the details given here, I'm just giving, see, when we are talking about the total consumption in our inference, we talked about this DRAM access part. Now we are coming to this actual computation. Okay, that is we are doing in our actual hardware. That's why this is EHU. Okay. Now this, when we are talking about this hardware computations, what we have, what we are doing some computation. For that we have some energy consumption. We are accessing some weight. We are fetching some weight. We using some store weight. Again, maybe storing and basically for weight we should consider fetching and reusing. And this is for our actual input. For that, we are again fetching them, storing them back. Intermediate activation values, we are actually activation outputs, incurring some energy. We are that is also contributing to some energy. So when we are considering the energy requirement or energy consumption, overall energy consumption in our hardware, we have, it is coming from our computation, it is coming from our weight access, it is coming from our activation input, output, storing and accessing. Okay. Now come to each of them in detail. When we are talking about the computation, this computation, as you know, that it is related to our MAC block, right? Multiply accumulation block that we are using. Is that quantization bit is basically controlling how much energy consumption is there when we related to that energy we are considering as EMAC, on which is taking effect on qubits. Okay, then this is the, that means how many times you are accessing the blocks. Based on it, this is for each time you are accessing the blocks with some qubit input values. For that EMAC Q into NC, how many times you are accessing them. Based on that, these total value will contribute to the global consumption. Okay, then everything what I am telling you is AS is the total number of intermediate output features throughout the whole network. This AS, these particular operations, we are basically considering the biasing, batch normalization, energy consumptions. Operations. The numbers we are accessing number of times for this biasing, the batch normalization, activation. These we are also implementing with some high precision. Maybe we are fixing that. Okay, we will be doing that with a 16-bit value. So for that, that we are doing on 16-bit precision value, and we are doing our Mac units, because that is our basic hardware. So for that, we are checking how many times those this energy consumptions are taking place. That's why 3 into AS into Emac 16. Okay, so this part is coming related directly for our considering, for our convolution, for our batching, for our activation functions, and also adding the bias. So this is the main computation, computation related energy. Other than that, we have these two values. That is, one is related to the weight, accessing the weights. Again, the accessing the weights, you can see here how many times we are accessing. Based on that, EM is the, because this, when we are talking about fetching of weights or fetching or storing of activation values, that is related to the energy that we are considering, that is energy related to memory. Okay, EM into NS, how many times you are doing. Okay, so that is the number of times you are accessing the memory, plus this EL. This EL is, if you go back to this diagram, as register. That means in general what we do, we store the related data in this memory. Hello, am I audible?
Yes,
Sorry, my net got disconnected. Okay, so someone is raising hand, right? Who is that? Hello, can you hear me?
yes, ma'am.
Okay. So Kanchi Venkate Sai Rusil, you are raising hand. Is there any question?
No. It was just to like say that a voice was breaking. Like everyone
Okay,
was having
okay.
a report.
Yeah. I was also I was in full screen also. I have not observed. Okay, so just let me know how far have you listened. I was explaining this one. So was I online till I mentioned about this EHW? I mean, how far have you listened? Can you tell me, someone?
I'm still not visible if you have shared this.
The slides are not visible. Okay, actually, today the net is very bad. Just wait. Okay. Are the slides visible now?
Yes, ma'am.
Okay. So can you tell me how far we have discussed? I mean, how far you have listened? Have you listened?
You were explaining.
Pardon?
You were explaining about EL and EM in EW.
Yeah, right? Okay. Okay. So, okay. So for the EL, what I was telling, that EL means this intermediate energy consumption. We are storing our related weights and activation inputs, outputs in this SRAM. Okay. From there, as per our computation, we generally fetch some related values in the local memory that generally we term as register. So when we are fetching something from the register, because register is the fastest memory. So from there, when we are whenever we are fetching something from register and we are using that for computation, that energy consumption we are terming as EL. Okay, so yeah, that's why. And in EL, you can see how first you now that you understand that how many times you are accessing the register. That you can get the idea from this NC divided by root over P. Now this P is the reduction in memory energy. See this reduction in memory energy due to activation level parallelism. Okay, that means you have taken one data in this register and this value you are using in parallel for multiple computations. So that way you are actually applying that parallelization and you are reducing the requirement of this EL. That means if it was a direct NC times of a EL fetch, then EL into NC, now you are applying some parallelism and then you are reducing this part of memory. Okay. So similarly, when you are talking about this activation input storage and fetch, the same thing. Only one small difference you can see here, EM into AS, okay, number of times into the memory requirement into 2. Because in this case, when we are talking about activation inputs, we are fetching them as well as those activation outputs, we are storing back them in the memory to be used in the next layer. So here, this for this weight, we are just fetching because we are talking for the test layer. We are talking about the test phase. So there we are for weight, we are just fetching the values. But when we are talking about activation EA, activation input related energy consumption, there we are talking about load as well as store. Okay. So you are loading, you are fetching and you are storing. That's why 2 into the same value. Rest you can see, rest everything is same. Okay. Because you are fetching from the register, but when you are storing back, you are storing back in some memory location. So that's why this 2 factor. Okay. So this is the this is the factors that is contributing to our global energy consumption. And now as you understand, we will see more that we were talking about this part, this EMAC Q. When we are reducing that Q bits, of course, my energy reduction, this energy related to this MAC operation will be less and overall computation energy will be reduced. So when we are talking about the sparsity, when we are talked about basically in sparsity and pruning, we try to reduce the number of weights or number of activations, and we try to remove this some EMAC values, because when there will be no operation, of course there will be no consumption of energy. So some EMAC values you can actually omit. But in quantization, what we are trying, we are controlling this value of Q bit and we are trying to reduce that EMAC as much as possible. Okay, so this is just to note that a 2 MB memory stores more than 1 bit weights, but only because the point to note here that when you are considering some weight in 1 bit, of course you can store huge amount of weights. The number of weights will be more. Whereas when you are considering 16-bit memory, sorry, 16-bit size of your weights or your activation inputs, outputs, etc., the number of weights or number of activation values you can store actually much lesser. So this is a very salient point. So now what is the main limitation you have observed here? Can you tell me what is the main limitation you have observed in this time Q&A? Anyone? Any observation that you find maybe not today, maybe last year? Okay. So one graph we were discussing here. Yes. And here we have observed that for a sudden change, we have to increase or decrease this quantization bit slowly. And for a sudden change, your accuracy may change abruptly. This is one thing. That means when you have decided not to do any quantization in your training part and you are applying quantization only in the test part. For that, you cannot plan for a typical hardware and you cannot plan that, okay, for only this much of bits, for a very specific qubit, I will realize my network. The reason is that way you have not trained your model. So suddenly if you fix some Q value according to the availability of your hardware underlying platform, then you may not get the accuracy as you want. Now that problem can be solved in train-time quantization. That means from the initial point, from the training itself, you are considering some low precision, and with that you are training your model. Based on that, you are having some weights, you are getting some weights, and these weights you can actually use in your testing phase. So that means you can also plan, okay, everything I will do within a particular, maybe within 16 bit or some 8 bit. Maybe I have some 64 bit data, doesn't matter. I will quantize that from the training phase, and end to end, the hardware I will develop, the accelerator I will develop, that should work in 8 bits. Now 16 to 8, even I am telling, we can do the same thing in 1 bit also. At the end of our discussion, maybe that will be our last discussion. There we will talk about this 1 bit network topology. 1 bit CNN network topology, how it works, what is the accuracy, and what is the practical application. That means we can also do everything in 1 bit. And what are the things we are mapping or we are scaling down to 1 bit, that we'll discuss, and what is the effect for that in the accuracy. But that we can only do when we are considering train-time quantization. Starting from training, we are involving the quantization, and according to that, we are getting the weights. According to that, we are getting our training model, and we are doing the inference. We will see that in detail. But that will be the last discussion. That is our ultimate objective. That okay, within 1 bit also we can do CNN, we can get some achievable accuracy that is meaningful for some particular application, and that we can realize in our embedded devices. But as of now, as I mentioned, whenever we are reducing, I mean, you are doing some quantization, you are applying some quantization. Let's say you are observing that in the quantization you are applying, up to 5 bit you can go. I'm just saying one example. Okay. And every operation, addition, subtraction, multiplication, all the filter related operation, batching, everything you can do, all related operations you can do in 5-bit. But the problem is the existing hardwares that you have, there you are not getting any support for this 5-bit architecture. Though you can operators, it would have been better that you have some 5-bit operators like 5-bit addition circuit, 5-bit subtraction circuit. That will give the maximum advantage of your 5-bit quantization. Otherwise, what is happening? You are doing the quantization because you can check that, okay, up to 5-bit, whatever accuracy is I'm getting, that is okay for my application. Maybe if you do 8-bit quantization, their accuracy is more, but you are not using that accuracy, you are not getting that, losing that accuracy. On the other hand, whenever you are going to get the implement that 5-bit implementation in a market, in practice, you do not have any CPUs or GPUs, underlying platforms, where you can actually realize this 5-bit architecture efficiently. So for that, what is the objective? The objective of what is the solution? The solution is that designing application specific integrated circuits. I'm not discussing here how we are designing that ASICs, but you remember in our first class when we discussed the basics of embedded processor, we talked about this. So this is the importance of ASICs, that whenever you can go for a particular application, maybe a particular wearable devices, your smartwatch. There you are doing just one sort of machine learning algorithm. So that is very application specific. There it is sufficient if you have some 5-bit hardware blocks, because for that application it is sufficient. It will give the acceptable accuracy, and you can also, it will also support the related energy requirement for that wearable devices. So that way it is good to design, it is effective to design some ASIC basic chip. That means some ASIC circuit that may realize that application specific circuit will actually, that IC will only realize that quantized network, and it will handle your prediction. Okay, so based on that, what you have, whenever you are thinking that, okay, I can only go up to 8-bit or 16-bit, then it is better to use some existing microcontrollers, microprocessors, where you can that microprocessor, that with that you can map 8-bit network efficiently, 8-bit quantized network. But when you have to reduce more, or you can reduce more, there this ASIC implementation is good. That way we choose our embedded processor. Okay, next on the sleeping part. Maybe this same equation we have seen in our training, sorry, testing level quantization also here somewhere. Yes, and that time we just skipped. We told that skipping that this is yet another algorithm, and we will discuss it later. So this clipping, basically this quantization, this is the same thing we do whenever we do this quantization. Clipping means nothing but chopping. That means you have this sort of thing. You have one width, maybe you have decided one range. Okay, I will go from -1 to +1, and that way I will apply some algorithm clip on that weight, and that weight will get mapped to within that interval. But in general, when we do clipping, one important part we add is a scaling factor. Okay, this is our scaling factor. Now, this scaling factor is an important part because that scaling factor maps efficiently whatever you have in input data and whatever you are getting after your quantize. I mean, after you are applying the quantization. Okay. Now, the scaling factor, basically you are adding, you are multiplying it with some power of 2. Okay, and then you are rounding off. See, if this Q, if you are considering some 8-bit quantization, that means you are multiplying this W with 2 to the power 7. Then you are rounding off, and then you are dividing that with 2 to the power 7 some values, and that way you are adding one scaling factor. And you can always check, because that you can do one if you apply Q is equal to 1 here. 1 minus 1 is 0. So basically this is same as doing this W, rounding off this W, and then mapping and that is rounding off the W, and so that you can get in such a way when you are applying the clipping algorithm, so that you can get your values within this particular range. Okay, so this is clipping, means you are chopping the values, but that is a scale clipping from your input to output. Okay. So this is about how you are modifying the weight. Next, or weight, not only weight, also your activation inputs when you are talking about clipping. Next one is you are also applying quantization on your activation function outputs. And that you are doing basically here, if you are considered that you are applying this quantization on your activations, basically you are putting, providing the input to your activation function as a quantized input. Okay, so we are applying quantization on the weight and input values at the input of the layer. Also we are, if required, because if intermediate values are not properly quantized, so we are applying some intermediate quantization when we are giving input to our ReLU layer or the final activation layer. So if we do so, of course, after doing this quantization, we know that it will choose between max 0 and this quantized value. And if it is this quantized, this QA output is a negative value, it will choose 0. Otherwise, QA is already quantized, so it will choose that quantized value. So now whatever output in this way, whatever output we are getting in the activation, that is also quantized. So this is how we are controlling the quantization in activation. Okay. Similarly, in input layer, what we are doing, as we have seen, that whenever you are doing a particular quantization, okay, this is my quantization bit and this is my M input bit. This is easy to understand. This XN, those are the, like, your, if you represent them in a binary form, that means X0, X1, X2, and so on. Okay, you have this X values. Now these X values, you are basically representing, you are not choosing them. Like in binary, what we do, we consider the coefficient of these values. But here we are not, we are taking the 1100, maybe some bit level quantized value, the quantized value of these coefficients. So that's why you can see you are considering Xn into WQ, where n is running from 1 to m by q. And along with that, you are choosing the coefficient this way, this quantized way. So the main thing is that the idea is you are considering maybe if you are qubit quantization, you are considering qubits q0 to qn minus 1. Okay, so q minus 1 bits are like this. B0 you can write to BQ minus 1. Okay, all the bits and their n minus 1 values were taken. So 10 values are possible, and then you are taking for the chunks, you are quantizing and you are representing this polynomial in that way. Okay. So that way you are applying this quantization in the input layer, you are applying the quantization in the activation layer, and you are applying the quantization in the weights itself. So that means you need one extra quantization layer that should quantize these intermediate values or weights or activation values. You can see this that way your hardware or your model is now getting modified, where we have this quantization convolution layer. We have now batch normalization. After that, we have this quantized activation. Now you know that how we are applying quantization on that activation layer, then max pooling and so on. So based on your this filters, this how many times you are repeating, that is changing. See? So basically the main thing is that here you are actually applying, you are adding one extra hardware, adding some modules, some circuit that is doing this quantization. You are incorporating them along with your activation, along with your CNN module. Of course, there is some extra overhead to add that hardware, because that is also operating and consuming some amount of energy. But overall, since you are working on a lesser number of bits, when you had your inputs as m bits and now you are working on q bits, so there is this q is less than m. So overall, your mac related energy, it is working, your mac module is working on lesser number of bits. There you are gaining in terms of energy, overall energy consumption. Okay, so this is about what we discussed about our training and testing quantization. Okay. Now, one second. Now whatever we do, of course we have understood that we are working gaining in terms of energy. We have used some simplified arithmetic units, and we are also getting some acceptable accuracy. Okay, but to do this process, we are sometimes we are reducing the overall network statistical efficiency. What does it mean? Means that a CNN may require fewer training examples, and that way it is statistically efficient. But here we are reducing the statistical efficiency, and we require huge greater number of examples to train your model when you are working on this quantized scenario. So this is one limitation. And this is this is the way in how we can apply quantization, add quantization in different phases of your CNN network. Another simplified neural network, it is in continuation, just telling, that is called the cluster neural network. Maybe in our first slide here, you can. So far we have talked about this. We have talked about post-train quantization. We have talked about quantization aware training. We know what we mean by saturation and non-saturation in our activation function. And now we will be talking about a small thing, that is our clustering of weights. Because we have seen, can you tell me why this clustering of weights can be effective? Anybody? Clustering means nearby weights you are grouping together. You are representing one value of weights for them. So what may be the advantage?
There will be weight sharing, so less storage will be required.
Exactly, less storage, and not only less storage, less computation. Like whenever you are computing for that, we talked about that for that same weight, you will be fetching just from the memory. That we discussed about the memory fetching in the cache related discussion. You will be fetching that weight only once, and based on that weight you will be computing. So that means this computation related loss during your cache miss, and then extra again fetching that value from the memory, all this computation related time will be saved. This is one thing. And computation related time as well as energy, memory access related energy will be saved. And also, as you have told that memory storage will also be saved. So it will be a gain in terms of both in terms of memory storage as well as energy as well as computation time. So yeah. So what we do in clustered computation, from as the name suggests, maybe you understand that clustered quantization means a floating point network is compressed by clustering its weights and activations. Okay. It may happen you are not reducing, changing the value, you are maybe maintaining some floating point values itself. You are not changing the values from floating point to integer values, or that floating point values you are rounding off to nearest integer. That is also possible. But whatever may be the case, you are clustering or grouping those weights and taking the benefits of weight sharing. Okay. So what type of clustering we generally use? We generally use here this k-means clustering. Okay. With that k-means clustering, we cluster into n. I mean, we cluster them into maybe n clusters. Then that n types of weights we use in our computation. Okay. So what we mean by k-means clustering? Those who have already done machine learning courses.
We learn centroids and we cluster each of the points by assigning them to one of the centroids, and we iteratively update the centroids, and finally we get one with the minimum.
Yes. Okay. So, so all of you do know k-means clustering, or should I mention it once here?
Ma'am, explain.
Explain. Okay. Okay. So in k-means clustering, it's we call it as unsupervised learning. So these terms, I hope you know that unsupervised and supervised. The first day we mentioned that which groups the unlabeled data set. Okay. So initially what happens, maybe you have these type of data. See, maybe some scattered data. And there is no level associated with. So from this scattered data, you have planned, okay, I will take, generate, I will prepare K clusters. Okay, that means I will put this data in K groups. These are my clusters. Okay. So how that is done? That is done based on calculating the distance. Let's say these data based on the particular distance between some data points, we take the lesser distance and we cluster them in a particular group. That way, first we form some groups or clusters, and then we consider a particular, someone your friend told that is a centroid, some center point that you may define that as the centroid of that cluster. Okay. Now let's say this is the training phase of your k-means clustering. Okay. Now you have one new data point in your, that you have to test. Test means here what you have to do, you have to check in which data cluster I will put this data. For that, what we do in general, once we already have this, we have already defined this k clusters, we generally compute the distance. Okay, that is my testing phase. We compute the distance, and we take the minimum of them. That means that is my closest cluster. Put this data point into that cluster. That is my testing phase. That is my final outcome, that I have considered this data point is coming into that cluster. And once I have incorporated some new point into that cluster, the final thing what I have to do, again I have to adjust the cluster. That means the centroid I have chosen before, the center point. You can think the centroid as the center point. This from where you will next, when some data is coming, you will calculate the distance. So that center point or the centroid, you will again adjust and you have to select that centroid. And then your now your new cluster setup is ready to accept and to go for another testing phase. Okay, so that is the basic steps. That is the traditional machine learning. We in this course we have mostly talked about uh, the CNN part. We have not talked about traditional machine learnings like regression, like general clustering. So this is one traditional clustering method, k-means clustering. So you can see in this flow chart that you have decided what may be the numbers of clusters, that is number of clusters, that's k. Then you are selecting the centroid. Okay. Then when you have a new data point, you are considering you are calculating the distance. So this distance calculation, there are different ways. Remember we talked about something called the norm calculation. Okay. So based on those norm calculation, we calculate there are different distance, Euclidean distance, Manhattan distance. When we choose them, our accuracies differ. Okay. So that is a separate thing. Just consider that somewhere we are considering the maybe the Euclidean distance or Manhattan distance, and we are calculating that distance. And if the distance is minimum, so then we are putting that point, incorporating that point to that cluster. If not, we are moving to the next cluster and we are checking where the distance is minimum. Okay. So this is the basic idea of how we generally do the k-means clustering. Similarly, when you have when in your training phase, in your CNN concept, you have weights. Now you consider the weight values as your inputs. Okay. Now you are grouping them. Maybe some maybe you have decided, okay, I will work with this k number of weights. So according to that, you have grouped them, and finally, once that clustering is done, you are working with those the centroid values of those clusters. So that way, with that grouping concept, you are basically reducing the number of weights that is actually contributing, though those are generating, taking the effect of your actual weight values, but the weight values that is actually contributing to your computation, that is, number of them are first of all very less, and they are giving some result that is close to accurate, because that is there while you are generating those values, the final weights, then you are considering the effect of original weight values, but they are not the actual weights you are using. So that way, of course, that is the concept of cluster neural network. You are sharing the weights for multiple computation. Okay. So this is the concept of clustering. So with this, we end our discussion about how we can compress what in which parts we should focus when we are compressing our network. Okay. So like if you want a summary that what we discussed after our first class test, the first thing after our first classes, we are mostly focused on how we can reduce the computation and as we know, if we can reduce the computation, we can reduce the energy requirement. Okay. So first thing we have discussed that, okay, consider the application, study the application, and if possible, divide that application in some hierarchy. And for each stage, you compute the precision, recall, these type of parameters for that stage, and predict some classes. Consider those classes, predict the outcome or members of some classes. Consider those classes as pass-on classes. Pass those classes to the next layer Again, apply some learning techniques, prediction techniques on that pass on class. That way you are reducing the members of that pass on class. You are reducing the number of inputs on which you are actually computing. This is the first thing we have discussed. This is the first simplest way of doing the hierarchical cascaded processing to meet our energy requirement. Okay. The second thing we have discussed, that not only hierarchy, because for all types of applications it is not possible that you will break them in some hierarchy. That is entirely, we talked about that term, that is entirely application dependent. Fine. Next, what we have discussed about the some strategies. Okay, now if I have to work with all the inputs, all the widths, and I cannot work with hierarchy, or if I'm working in a particular stage of hierarchy, again further how I can compress the network. For that, we have seen that if we can go for some weight sharing, if we can go for input sharing, how our because we ultimately, for especially for the convolution layer, we have to do huge number of multiplications. For that, if we do some similar type of sharing techniques, in which way we can gain. We have talked about that, how we are storing the data in our memory. We have talked about the cache memory concept. And there we have seen that if we go for some sharing technique, first thing is that we can reduce computation, number of computations, as well as we can reduce the memory fetch and access time and related energy. Next, we talked about the pruning. Okay, chop off some part. We have seen what maybe the strategies we can take when we want to do pruning, what we actually mean by pruning. Okay, and how it is actually affecting to actually effective to increase the sparsity. The third thing what we have discussed about the next the quantization. Okay, how we can apply the quantization, what will be the difference between test and limitations of course. Also these parts, I think when you are studying, you study in this way, that what you are understanding, ultimately whenever you are thinking about compressing one network to realize maybe some constraint scenario, or you are trying for energy gain, or at least not even you are thinking about energy gain, you are thinking about computation gain, then also what steps you may follow. Then we have talked about the quantization, yes, and what we can do in testing, and what is the limitation of testing level quantization. So, and what is the difference between testing and training level quantization? What more we can add if I incorporate to quantization from the training phase itself? That we have seen. Finally, we have seen, okay, there also finally we have some limitation. If we could do that quantization in training or testing, there the limitation, as we have mentioned here. So we are, losing in terms of networks some statistical efficiency. So for that, what we are doing, we are keeping our input activation, inputs, output, those intact, and we are applying. But this is effective up to a certain level. We are applying some clustering technique on our weights, and then we are forming our cluster neural network, where with the cluster weight sharing concept, we are reducing some memory fetch time, memory fetch time and related energy, and also reducing in terms of computation. So all these things we talked about, they are very, though we use them in traditional machine learning, or when specifically I'm telling you are doing your machine learning in cloud scenario. Okay, in cloud means, you know, right? Cloud means you have huge access to servers. You can pay a little bit of money, you can get some extra resource. Okay, run your model. It is not catastrophic. It is not something, total blockage. If you cannot reduce, or if you are not doing any pruning, or most of the cases, if you are not doing proper quantization, you can work on higher order bits also. But these are very much effective or very much of a high requirement, high value when you are going for that embedded scenario. If you do not go for proper quantization, if you do not reduce the bit size, memory overhead, energy storage, energy requirement, memory storage, if you do not reduce them, you cannot actually realize your model in that that embedded platform where you have very much small amount of resources, small memory, small computation units. So, and also you have to finish your task within a particular deadline. So you have some real time constraint. So these I mean this techniques what we have discussed so far, it is very specific to embedded and very effective to embedded scenario. But finally, we will conclude this discussion mentioning one relation. Maybe this term regularization, you all know. And what is the relation with that regularization with sparsity? Now, when we talk about regularization, that is a very common technique. Can anybody tell why we use regularization? Have you heard about this term regularization? Hello, am I audible?
Is it to avoid
No.
overfitting?
Yes, to avoid overfitting. Correct. Anything else? You can comment on that. Okay. Okay, I'm explaining. No problem. So this regularization, we do not, generally consider keeping embedded system or embedded scenario in mind. This is a very general machine learning technique that you are correct that we use when we try to prevent this overfitting. Okay. Now overfitting, I think so far you all know that when we talked about overfitting, what we mean that I have got a particular model. Maybe this is my model. This is my best fit line. I have some inputs in. I have trained with them, and I got some model. Now, what we mean by underfitting, that means this model is giving error for both the cases in our training phase as well as for testing phase. In both the cases, this model is not working properly. That means maybe I have to train more, I have to add some extra data, extra features, and then I have to tune the model to get that exact, it's exact the parameter values, exact, maybe if it is a straight line, it's exact slopes, etc. Okay. While we are talking about appropriate fitting, appropriate fit or perfect fit, so there your training and testing in both phases, the errors are not so high. That means whatever training points you have, according to that, you have got one model. And when you are getting your test data, now the point on your test data for a particular, maybe for a particular X, the point you are getting on your model value and the actual point you are getting, the difference there is maybe you are getting some negligible error value for them. So that is appropriate fit. It may not be exact zero value of error, but very negligible error value. So that is perfect fit, appropriate fit. When we are talking about overfitting, that we have already discussed, it is working good for your training phase. That means it is going maybe perfectly passing through all data points, perfectly holding all your data points. It is satisfying for all your data points or training data points. But when it comes to for your test data, it is showing high error value. There is a huge gap between your model and your test data point. So if that error is high, test time error is high, we consider that as overfitting. Okay, correct? I think this we already mentioned before. Now what we do in regularization? In regularization, we consider one model. Okay, better I will come to this later on. Better I start our discussion with a simple linear regression example, that what we do actually in the regularization. Then I will come to this very, I mean, exact keywords, that why we want to do number of features or variables in the model. We actually, that very in a basic way we mentioned that when we want to get rid of overfitting, sometimes we chop off some features or we chop off some variables. So that way we try to get out of that overfitting. Okay. Now for this discarding, when we are doing the discarding, taking the step of discarding features, there is some associated loss of information. Okay. So maybe it is not using all the information, or it is not getting the effect of all the information we are having. Okay. So what we do in the regularization, could be used in such cases that would allow us to keep all the features while working on reduce the magnitude or amplitude of the features available. Okay. How we can reduce, I will come with that example just to get the idea that when we are doing that regularization, sometimes we are reducing the features, or one extended case, we are choosing some limited set of model parameters. Okay. Sometimes maybe you have also heard another term that is called feature selection. Okay. So that way, that is called a feature selection. We are not working with, sometimes we are reducing the size of the features, magnitude of the features, when we don't want to lose any features. And if you want to lose any, we can allow to remove some of the features and to avoid overfitting. That term is called feature selection. We will see with examples. But whatever we do, when now just get the idea why I am telling in this context of sparsity or weight reduction, what we know, what we already discussed in context of our energy gain in our embedded scenario. Whenever you are basically doing the feature selection, if your output is based on maybe in some this way, some weight and some input, some weight and some input, and so on. So if you are getting some weights, if it is tending to 0 or this is almost 0, you are basically removing these weights. You are setting these weights to 0. You are removing these features. That way you are selecting your features. That is called the feature selection. The selection that you are really selecting the base features that will actually contribute to generate your outcome or to decide your outcome. Okay, so regularization maybe can indicate to both the things. Maybe you are reducing the size, magnitude of the features available, or you are actually deciding, you are working on some limited model parameters. That means you are deciding some parameters you can throw out. Okay, so that is the concept of regularization, and that way it is basically, we have in ML we have considered that in ML we have used, we heavily use that to handle overfitting. But you understand, I think now whatever discussion, that's why I have taken it at the end, that if I actually can throw some parameter values, if I can set some model parameters as 0, we are basically reducing the related computation, related energy consumption, related memory overhead related to that parameter. So this is one sort of sparsity actually we can introduce in our embedded domain applications, embedded domain ML applications. That way regularization is also very is a requirement. Okay, maybe it is not so much, I mean, what I mean to say, if you are not getting any significant overfitting, it may happen you are not thinking regularization perspective in your general application always. But when you are coming to this embedded scenario, embedded ML scenario, this regularization is also one key block, that key operation that you have to consider, because that way with that regularization or a proper feature selection, you can check the options that if can I reduce more, can I throw out some more parameters so that that will give me some advantage in terms of energy or memory access. Okay, so that's why we are in that context, we're discussing regularization here. Okay, now what we do in regularization, we basically impose a penalty on the model to damp the magnitude. Okay, and based on that, how we are adding that penalty, that way we basically name this regularization techniques. One is lasso, one is ridge regression. We will talk one by one that what is the difference between them. But thing is that whenever we are doing this, we are thinking of regularization, we are adding some penalty. Okay. Okay. So you may relate that. I will come to this part. What is the difference of this penalty and come back to this diagram. But you remember when we talked about penalty-based pruning, there I have quickly skipped one slide that talked about penalty-based pruning, where the goal is to the same line you can find there also. Goal is to modify an error function or add another constraint, known as bias terms in the training process. Basically, there also with the error function, you are adding some penalty, and that way you are modifying the error function. So that is this. I have not discussed how we can add the penalty or what is the structure of this penalty or form of penalty. So you can relate that discussion here also, because the way I will be discussing the adding that modifying the error term, the same thing we can do in pruning also, while we are thinking about penalty addition. Okay. So I will explain this later on. Let's come to this. This is a. Can you see this, or I can just draw by my own? You can check this. Is it clear, this writing?
Yes, ma'am.
Okay. Then I'm not drawing again. Just this is my handwritten note. Okay. So since when we talk about CNN, what we do the same thing. We are applying filter, and that filter we are extracting some information. Then we are checking some outcome if it is matching with our predicted value or not, etc. Okay, so I will just explain this regularization, because if we go with that CNN discussion, my filter size and my weight size is huge, so it will be difficult to explain. Okay, that's why I'm just starting with the basic linear regression. Okay, what we'll do, when we talk about multiple linear equations or linear regression, we have some this type of some points, data points I have, and we are getting with we are training with our training data, and we are getting a particular model. Generally, we call that as our base fit line. Okay, base fit line. So the idea is from the points on this line, our training points are the difference between our training points are very less, very negligible, and in ideal case, this is basically maybe this is my training line, and this is my best fit line. Okay, if I'm able to get it. Basically, this is a straight line, so you can understand the equation will be y is equal to mx plus c. This m will be the slope, and this is the concept or bias. Okay. Now, if you take one multiple linear equation, that means you are in your problem, in your practical problem, it may not happen that your outcome y, it is only dependent on a particular feature. Let's say you are doing that this medical related on some data set, you are doing some cancer prediction. Okay, so that cancer prediction may depend on various medical parameters, age, many other medical parameters. I don't know the name of them, but maybe you are denoting them by x1, x2, etc. Okay, so those are your inputs. Associated to that, you have some weights. You can tell them as coefficients or weights, and then you are getting your outcome as y. That is your, when you have trained repeatedly, you got the values of this beta 1, beta 2, etc. Those are your weights. You got the weight values, and based on that, you have got this equation. Okay. It may happen the whatever I have drawn here, exactly the line is passing through your all the points. It may lead to some cases, it may lead to overfitting, right? That means when you will understand, it may lead to overfitting. Now let's say this is your test data. Okay, for some test inputs, some x1, x2, x3, this maybe this is a vector value, x vector. You are getting some output y. So this is your test outcome. So you can see there is a gap between, for a particular x, there is a gap between this is your test output and what you are supposed to have in your, this may be y hat, what you are supposed to have in your model line. Okay, this is your model line. We are thinking about this linear line. Okay, so you are having this, there is a gap. Okay, so what we do in our general concept, this y minus y hat or y hat minus y, this is our error. Okay, or sometimes we term it as loss. In various cases, you will find these terms, but they mean the same thing. They indicate the difference between your actual outcome and your predicted outcome. So that is the difference. Okay. Now, what will be your cost function? Cost function means the function you are forming, what you want to do. Okay, you want to reduce this y minus y hat. Okay, this what you will do, you are taking multiple points, you are taking the sum of square form. That means you are taking for yi minus, sorry, it should be yi minus y hat, and you are for I is equal to 1 to n, you are considering this sum of residuals. You can see here, this is your sum of residuals. Now, why we are talking considering these form, there is some other advantage I'm not going to discuss. I mean, that will take time. So we are taking this, and what will be our objective? That reduce this cost function, reduce this sum of residuals. Okay, this is our objective. Okay. Now to do that, in general, what you will do? When you are actually trying to reduce that cost function, that means you have this line. Now this is your model and your predicted value is maybe here. This is your predicted value. Okay. You want to reduce this gap. That means you are changing the line. Maybe you are changing the slope of the line. Some line that will go the path or that will reduce this gap you are trying to find. And of course, it will be better. The minimum, the gap, that will be better. Okay. Now you observe, when you are doing that, okay, what you are doing, what is the technique? You are using with, as in our penalty-based pruning also, you can see here, we are modifying the error function and adding some constraint. So here you see some constraint we are adding. Okay. Now this constraint has some two parts. This is one part that is controllable. You can learn again more and more, and based on that, this controlling these factors, you can basically change this slope in such a way that you are, what to say, you are reducing this gap, because you want your model will be better, your model will be effective when you can reduce this test time error, right, as far as possible. And also the other part is, this is a function of slope, your existing slope. Now, when you are changing this slope, okay, you are changing this slope and you are controlling this parameter, okay, your line is coming closer and your gap is reducing. That is, your objective is going, it is satisfying. But what do you mean? Now you see this multilinear equation once again. Okay, see this one. Okay. When we are talking about the slope, this slope is basically depending on these coefficients, beta 1, beta n, etc. Okay. If that is so, that means whenever you are modifying the slope, there is some modification in this beta 1, beta 2 and their relations. Okay. Now, there are two terms I should mention first, that when we are talking about ridge regression, as we mentioned in here, this is L1 lasso and L2 ridge. Okay. When we are talking about these two different types of regressions, basically we are considering this relation, okay, this slope that is in ridge regression, that is dependent on this sum of squares, whereas in lasso you can see the change is here. It is the weight or coefficient values, they are additive. Okay, based on that we define this function. Basically, in what parameter, what penalty we will add, that will be dependent on some controllable parameter, this lambda, along with some relation between the weights or coefficients. Now, based on the regression process we are choosing, based on that, intermediate relation between these weights, that will change. This is beta 1, beta, this is sum of squares, this is additive. Okay. Now, this way, so this is the basically when we are now, if you again extend a bit, you are changing the slope. You are reducing this slope. That means you are reducing these parameters also. This beta 1, beta 2, you are reducing. And you are still checking the outcome, your value, and you are checking the accuracy, etc. It may happen if in case of your multilinear scenario, multiple linear equation, you have multiple beta 1, beta 2, sorry, beta 1 x1, beta 2 x2, and so on. Beta n xn, so many coefficients. You are adding, you are considering their additive relation, and the whole thing is basically degrading. Your slope is totally degrading. It may happen some of these weights, they are becoming, if some beta values, they are very huge, they are shrinking to some particular value, or some beta values which were already very small, which were very negligible values, but not zero that time. Now, due to this shrinking procedure, they are turning to zero. Okay. If they are turning to zero, that means you are basically removing the effect of this feature x2. That means you are removing the consideration of this feature and you are considering these other features, maybe beta x1, xn. You are checking that you have applied this considerable penalty. You have shrink those parameters. Still, they are contributing to the outcome. Still, they have some significant coefficient values. That means they are actually contributing to your outcome generation. So that is called, that features you are selecting. And that is called the feature selection in traditional machine learning. Why I'm telling this much? Because when you are, as I already mentioned, when you are actually applying any this type of regression, lasso regression or ridge regression, and you are applying regularization, that then I'm going back to the slide again, you are imposing a penalty. There is a shrink, you are modifying the slope of that your model. You are modifying here in this case, because we have just considered a straight line. We talked about in this about the slope, but this is not about slope, because when we are moving from 2 to 3D or we are considering some more features, then it will not be about the only the slope, but the main idea is whenever we are modifying we are applying this regression techniques, we are applying some penalty, there is a reduction in this weights, and these reductions may or may not be so significant that may incorporate some sparsity in your design. And if you are lucky enough, you are getting some sparsity, you are checking that, okay, I can get suitable outcome with not so significant accuracy loss, but there is no need to consider few of the weights or few of the features. I can do that feature selection effectively. That will help me to realize my model in my embedded scenario. Okay, so that way there is one indirect relation. Maybe we do not do this regularization to handle this sparsity or to incorporate sparsity. That is not our objective. Our objective to reduce overfitting, but to reduce the gap between your prediction and your actual data. But doing that, in turn, we may reduce the shrink the parameters in such a way, model parameters, that it may lead to some sparsity and give us the advantage. Okay, so is this part clear? I mean, why we are talking, why sometimes regularization may be effective and may help us to introduce sparsity in our design. Okay, so about this diagram, you can see it is basically the plot of you are considering. If we are considering these two plots, two beta 1, beta 2, these two weights or coefficients. Okay, so this is the lasso plot for your lasso regression, and this is the plot when you are considering this beta 1 plus beta 2 and you are considering them a particular threshold, less than a particular threshold. Whereas whenever you are considering ridge regression, you see you are considering the relation beta 1 square plus beta 2 square. That means it is forming a circle. Okay, now you consider this tip. Okay, now this is the contour for sum of residual. Okay, you are doing, we talked about the sum of residual. You are plotting, you are getting multiple sum of residuals, and for them you are plotting this weight related relations. So you can see when you are actually here, for these point, these contours are meeting with your lasso regression, and at this point one value of your weight or coefficient is basically 0. Okay, this diagram signifies, but if you see this ridge regression, this contour is meeting here. It is not meeting at any of the edges, any of the axes. So for that reason, it is this value, you are not getting any value, non-zero beta I value here. But here, some beta I value, that is 0 value. So that way, to introduce sparsity, when we actually apply regularization, we have both the choices. In general regularization, we can apply lasso or we can apply ridge. That means we can apply this additive relation or we can apply this sum of square relation. Both are right, both are possible. Maybe in some cases ridge works better, etc. There are some advantages. But when we particularly want to get some sparsity, we want to go for feature selection, and we want to check which weights we can actually remove, for which coefficients we can actually get some 0 values. At that time, this lasso is better, because from the plot you can see it is meeting with this contour at a certain tip point where one of your weights may be 0. Coefficients may be 0. So you can throw out that feature, you can introduce sparsity, and you can save in terms of your energy requirement, memory requirement, etc. Okay, so this is the last point where we are considering regularization, but our objective is not to introduce sparsity, but it is eventually we are getting in terms of some sparsity. Okay, is this part clear? Do you have any question? Should I repeat? Just go through this part. If you have any question, just let me know. Okay. So up to this will be your syllabus. So next Tuesday there will be a test. Okay. If you want to ask me anything, you can ask. But I hope just this point I have explained to show how this regularization, this operation, how it is related to sparsity, and eventually you can gain something in terms of sparsity if you apply regularization. Okay. Am I audible? Are you there?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. So just go through it. If you have any question, ask me. Otherwise, to that, we have completed our discussion about how we can shrink our network. CNN network, what are the possibilities, what the operations we can apply. Next, after your test, we start something else where we will see that how, like, here whatever computations you are doing exact computations. Okay, you have to do a convolution, you are multiplying with your filter values, you are multiplying with that, you into the multiplication you are doing exact 2 into 2 you will get 4. But what we will see next coming discussions, if we sometimes get 2 into 2 3, that is also okay for to get our final outcome. So we will talk about something called approximate computing and how it is important for when we are going for energy saving, we are trying to reduce our computation time, etc. Okay, that we will start next week. Okay, if you have no other questions, that's all for today. Okay, about the deadline, maybe they have updated. I will see. You got that one assignment yesterday, the assignment, right? Related to activation function that you try to finish within 4th, because that will help you in your exam preparation also. Okay, and the second thing is that about that other TinyML related assignment, try to upload that within 10th. Maybe they have already set the date. Okay, so that's all for today. If you have any other question, you can ask me. Otherwise, we can wrap up the class. You may leave the link if you have no other question.